of quantization per se, or geometric quantization per se, but of the sort of formalism that comes before it, namely, or that grounds it, namely geometric prequantization. So the outline for this talk is as follows. First, I will give a very, very, very brief introduction, or a review, really, of geometric prequantization in the motivating symplectic setting. Second, I'll give a also brisk introduction to polysymplectic geometry and polysymplectic manifolds in the way that I have worked with them. And then finally, we will combine or synthesize the material from the first two sections to obtain what is one potential definition of a polysymplectic prequantization formalism. So really, the aim of this talk is just to, this very brief presentation, is just to motivate, from a purely mathematical perspective, the following construction, namely this definition of a prequantum vector bundle, where which we'll see will comprise of which on a V symplectic manifold. So here V is a fixed vector space, will comprise of three data. First, a Hermitian vector bundle E on M. Second, a fiber-wise V module structure A of V on the fibers of E. So this is a V module structure where V, we're thinking of it as a Lie algebra. And then third, a unitary connection nabla on E, subject to the condition that the fiber-wise V module structure A is parallel with respect to nabla. And then all of this data needs to satisfy the compatibility condition that the curvature of nabla as a endomorphism valued 2 form on M satisfies the what looks somewhat like the familiar curvature condition in the symplectic case. And then we'll see what this means in the final section. Okay, so part 1, geometric prequantization. So I'm not going to review what a symplectic structure is. This is the 5th talk in this conference. But I will make a comment on Hamiltonian symmetries. So on a symplectic manifold, we have a map from functions F, which we can think of as classical observables. If we're thinking of the symplectic manifold M as a classical phase space or momentum phase space, to the Hamiltonian symmetries, or the symplectomorphisms, infinitesimal symplectomorphisms of M. So these are vector fields that preserve, that under whose flow the symplectic structure omega is preserved. And the relation between F, the classical observable, and X, its induced symmetry, is given by this characteristic equation here. So the exterior derivative of F should be the negative contraction of the symplectic structure with X. And depending on our conventions, this negative sign might be a plus sign. So when this relation obtains between F and X, we say that F is a Hamiltonian function of F, and X is the Hamiltonian vector field of F. So every function F has a Hamiltonian vector field X, but it's not necessarily the case that every vector field X has such an F, even if X preserves omega. And when such an F does exist, it is never unique. And then using this relation, we obtain a Lie algebra structure on the classical observables, that is the functions on M, given by the instantaneous change of H, of this function H, with respect to the infinitesimal symmetry described by F. Okay, so the idea for us, for the purposes of this talk, the idea of geometric quantization then is to extend the symmetries, the Hamiltonian symmetries of the symplectic manifold M, that's this represented by this line down here, to the space of sections of a Hermitian line bundle L. So we have a classical observable F. It induces an infinitesimal symmetry on M. We want to extend that symmetry XF, that classical symmetry, to a quantum symmetry QF on which will act on the space of sections of this line bundle L. And so the space of sections of L are the well, we can say pre-quantum states associated to this configuration, whereas the points of M are the classical states. And also note that this map Q, which takes classical observables to quantum observables, it's a map of symmetries. It's not a map of states. So the quantization doesn't, just by the way, the quantization of M doesn't involve an assignment of quantum states to classical states. All right, so then the formalization of that idea is given thus, namely that a prequantization of a symplectic manifold consists of these three data. First, a Hermitian line bundle L on M. Second, a unitary connection nobla on M, which satisfies this curvature condition for some non-zero constant C. Sometimes we take that to be 1, sometimes 2 pi. This constant C is going to play the role in the real valued setting that the representation, the Lie algebra representation A that I mentioned earlier, plays in the general polysymplectic setting. And then third, the assignment Q, which takes classical observables F to associated quantum observables QF, where in particular Q is defined in this way. So we say then that the pair L nobla is a pre-quantum line bundle for or on M, and this operator is the quantum operator or quantum observable associated to F. Okay, so that's how fast we went through quantization. So next I want to describe what might be less familiar to everyone. That is polysymplectic geometry, and in particular the sort polysymplectic geometry in the way that I've tended to look at it. So first of all, we fix a vector space V, and then we define a V-symplectic structure on a manifold M to be nothing more than but a closed and non-degenerate two-form omega with values in V. So this is just a very, very, very easy generalization of the notion of a symplectic structure on M. We're just replacing the space of coefficients R with a general vector space V. So we can relate this to multisymplectic geometry very heuristically. Here's sort of a spectrum of similarity. So we have symplectic geometry on this side and multisymplectic on the other. And so I'd say that polysymplectic geometry is much more similar to symplectic geometry, at least insofar as it's generally very clear how to extend definitions and statements of results from symplectic geometry to the polysymplectic setting, even if it's not necessarily always clear how to resolve those questions, or what properties those generalized structures take. On the other hand, I at least have found that with the multisymplectic context, in the multisymplectic context, it's not always clear how to even understand the extension of how to extend a symplectic notion to the multisymplectic setting, how to extend symplectic constructions to multisymplectic geometry. Right, and then a very small amount of background. So this is a fairly natural idea. It's just vector valued symplectic geometry. It's come up many times in the past. The first that I'm aware of is by Awane, called K symplectic geometry. So in this formalism, we have K pre-symplectic structures on a manifold, on an underlying manifold M, and these pre-symplectic structures need to satisfy what we might call a collectively non-degenerate, collective non-degeneracy condition. Then Gunther has the more, or what I found to be the more popular polysymplectic geometry, which in terms of this V-symplectic formalism that I suggest on the previous slide, is just RK symplectic geometry. Norris developed N symplectic geometry. I think this is very similar to K symplectic. Marrero, Roman Roy, Salgado, and Villarino then had a sort of a nice paper in 2015 where they introduced a polysymplectic reduction scheme. And then the paper that I'm talking about, just to place it in this timeline, was from 2019. So I'll give now 3 examples, one that's quite easy, and then 2 that are somewhat more interesting. So besides the very basic case of symplectic manifolds, probably the most basic example of a polysymplectic structure is given just by taking 2 symplectic forms, omega 1, omega 2, and just pushing them together. So taking their direct sum, from which we obtain an R2 valued symplectic structure, or an R2 symplectic form on M in this obvious way. More interesting, and then maybe more closely associated with this notion of V-symplectic geometry, because in this case, it's less natural to deal with RK valued forms, is the following example, in which we take a Lie group with a discrete center G, and we let theta be the Maurer-Cartan form. So theta is a Lie algebra valued 1 form on G, which is defined in the following way. It's quite simple. So here's G, it's this, or the capital G, the Lie group, it's this circle. The Maurer-Cartan form takes a tangent vector x, and then, or based at an element little g, and then it acts on x by left multiplication by G inverse to bring, to take that tangent vector back to the identity. Well, the identity, the tangent space at the identity is naturally associated with the Lie algebra. And so that resulting value is the is what the Maurer-Cartan form returns. And so then the associated G Lie algebra valued Lie algebra valued symplectic structure on G is just the negative exterior derivative of theta. And then a final example given by these polyphase spaces, which we saw in or heard about in Tom's talk. Here we fix a smooth, or well, here we fix a smooth manifold Q, and we consider this. It's like a V-valued cotangent bundle over Q. So this is so here we have homomorphisms, linear homomorphisms from the fibers of the tangent bundle into the space of coefficients V. And then precisely as in the symplectic case, we have a canonical 1 form given by, and then illustrated down here, given by projecting a tangent vector x down to the tangent bundle of Q, and then feeding that pushed down that projected tangent vector to the base point of x. So then that gives us a value of that gives us a value in V, and thus defines a V-valued 1 form on this homomorphism bundle. So then in this case, the canonical V-symplectic structure is the negative exterior derivative of theta. And then, so more generally, these 1 forms theta, which bear this relation to the polysymplectic structure of interest, these are just the polysymplectic potentials. So in those terms, we can see that the Maurer-Cartan form on G is a polysymplectic potential for a very natural G-valued symplectic structure on G. Okay, and so then just as in the symplectic case, we have a Hamiltonian formalism. The characteristic relation is exactly the same formally. In this, so one difference between this polysymplectic setting and the classical symplectic case is that it's no longer the case that every smooth function h has an associated Hamiltonian vector field x. However, it is still the case that if it does, then that vector field is unique. And if a vector field has an associated Hamiltonian function h, then that function h is unique or precisely up to addition of constants. And then very interestingly, I think the space of Hamiltonian functions, so we'll denote that by C infinity h, this is still a Lie algebra with Lie bracket given by the same expression as for the Poisson bracket. It's not. This is not a Poisson bracket because it's not a derivation, or it's not a biderivation. And then we'll need one sort of technical condition just to make the theorems work later. And so that's the condition of transitivity, which states that, which when it holds, asserts that every tangent vector y on our polysymplectic manifold M extends to some Hamiltonian vector field x sub f on M. So that is for every tangent vector field, for every tangent vector, there's a Hamiltonian function f, the Hamiltonian vector field of which coincides with y. A consequence of this is that we can get from any 2 points on M by flowing along a time-dependent Hamiltonian vector field. Okay, so then the final section, I'll just I'd like to motivate the mathematical construction of a geometric prequantization that I mentioned in the beginning. So the idea is going to be precisely the same with the obvious substitutions, namely that we want to lift the Hamiltonian symmetries of M, now a polysymplectic manifold or a V-symplectic manifold, to the space of sections of a Hermitian vector bundle, E. So it's no longer a Hermitian line bundle, it's now a Hermitian vector bundle. And so this gives us a map Q from the Hamiltonian functions on M to the endomorphisms of the space of sections on E. And so we're identifying the space of sections with the infinitesimal transformations of E. So we're going to want this to preserve or to be compatible with an inner product that we're going to have. Oops. So then we have a preliminary definition, which won't be our actual motivating definition, because we'll see that there's something that when we just try to define it in the naive way, there are some deficiencies. But so the preliminary definition is that a prequantization of our polysymplectic manifold should consist then of a Hermitian vector bundle E and a faithful first order, that's a technical condition that I defined down here, Lie algebra representation Q from or of the Hamiltonian functions on M on the space of sections of E, preserving the inner product on the subspace of smooth L2 sections of E, subject to this condition, which I call the Hamiltonian lifting property for all relevant data. So this is called the Hamiltonian lifting property because, heuristically, that's what it asserts. It says that Q, so in this image Q, that if we were to drop these vector fields, if we were to push them down to M, they would give us back X sub F. So it's as if we're extending the flow of X to Q. And then of course these are acting, we're ultimately thinking of these not acting on points, but on but dragging along sections. Okay, so very quickly, a note on this first order condition. It's just very technical. I had thought actually originally that it would be implied by this Hamiltonian lifting property, but I couldn't show it. And then after a sufficient amount of time, I started to suspect that maybe it actually is. It might be independent, and so it just says that essentially that this operator Q has at most first order dependence on the functions f, so that if two functions f and h agree at a point x on M, then QF psi for some section psi and QF h for some section h have to agree at x.
Casey, just a few minutes left.
Oh, really? Oh my gosh. Okay. Okay. So then the problem is, what does it mean to be L2? Because in the symplectic setting, there's a natural measure on the base, namely, we take the appropriate power of the symplectic structure, and this is unique up to rescaling. And when I say a unique measure, I mean this is a unique measure that's preserved under all symplectomorphisms. Okay, so then this brings us to the question of invariant measures, which the definition is what we'd imagine it to be, namely that an invariant measure is just a volume form that's preserved by all of the Hamiltonian symmetries. Its existence is not guaranteed on a general polysymplectic manifold. However, if there is a non-zero invariant measure, and if M is transitive, then that measure is unique up to rescaling. In order to obtain an invariant measure, we might need to cut down our space of observables, because if we have too many classical observables, they might then it's more difficult to have an invariant measure. The smaller the space of observables, the easier it is to be invariant under the action of all of those symmetries. So we just define an algebra of classical observables to be any Lie subalgebra of the space of Hamiltonian functions, and invariant measures with respect to those algebras are defined in the obvious way. Okay, so then the motivating definition is precisely the same as our original naive definition, except now it needs to be taken with respect to an algebra of observables and a measure on M, which is invariant with respect to those observables. But then for the purpose of just for simplicity, we'll assume that the algebra of observables is the entire space, and that our invariant measure exists. Let me see. Okay, so 3 more slides. So we can consider the space of coefficients. We can consider the space of coefficients V as being the constant functions on M. So the constant V-valued functions on M, and thus they form a Lie subalgebra of our algebra of observables. And then for every constant function, we can show that this equality holds, which implies that, or for all real valued functions S on M, which implies that this operator QV is tensorial, which means that its action preserves the fibers. So this induces then a Lie algebra representation of V, so induced by Q, a Q-induced Lie algebra representation of V on the fibers of E, and in this way, E, the Hermitian vector bundle E over M inherits the structure of a bundle of V representations. And And then if the M is transitive, then this expression here, Q minus A, where A is the V module structure of E, defines a V linear covariant derivative on E. So V linear just meaning that that this commutes with the action of V. So putting that together, we see that acting by QV induces a scalar multiplication of V on the fibers of E, or just on E. And then by subtracting off that scalar multiplication from Q, we get a V linear covariant derivative nabla. And so final slide. This brings us to the notion of prequantum vector bundles. Now, in analogy with the definition of a prequantum line bundle, we define a prequantum vector bundle to consist of a prequantum vector bundle on a V symplectic manifold to consist of these three data. First, a Hermitian vector bundle E. Second, a fiber-wise V module structure A on the fibers of E. And then third, a unitary connection nabla, which is parallel, with respect to which the V module structure is parallel. And all of this subject to the condition that the curvature is given by negative the scalar multiplication with the scalar multiplication described by A, induced by pairing tangent vectors using the polysymplectic structure omega. So as shown here. And then the final result, the final theorem, is that if M is transitive and connected, then there's a natural correspondence actually between prequantizations in the conceptual sense that we motivated the definition of this Q. So the Q, these prequantization maps from classical symmetries to quantum symmetries, and prequantum vector bundles. So the prequantum vector bundles are certainly much easier to work with than these more, I think, conceptually appealing prequantizations, but there's no loss of generality by just taking the prequantum vector bundle first. And I think this is quite interesting because it applies in particular to the real valued case, which I found to be sort of pleasantly insightful for my own understanding of this material. And then the relation is given in the obvious way here between Q, the prequantization, and nabla A, the data associated to the prequantum vector bundle. And then there's some questions, but maybe we'll just send the slides to everyone at the end. But the most interesting one is just what happens when the underlying polysymplectic manifold is not transitive. I have no idea. So thank you. Yes.